So in this video, we're going to introduce the concept of minimal spanning trees. Now, before we can get into what a minimal spanning tree is, we need to actually understand what a tree means in the context of networks. Now, we've seen trees with probability trees and in other sort of branches in maths, but we are talking about specifically with networks, a tree being a connected graph. So a graph that connects a bunch of vertices with edges, containing no cycles, multiple edges, or loops. Now, just like when I did with probability, I'm just going to remind you of what a tree would look like in an everyday context, okay? Now, if you think about a tree has branches, okay? So these branches go out in different kind of directions. They can look sort of like this. And basically, it just looks something like this, right? Our branches just go out in different directions. Now, imagine this as a network diagram where all these little branches sort of connect and change directions. We can think of these as our vertices by just drawing these dots here. Now, what a tree doesn't have is a cycle, for example. So the branches won't ever connect back up together in this particular way. A tree doesn't really look like this. A tree also won't look like this, where it has sort of something like this and an edge here, and it contains a multiple edges like this. We don't typically see that with trees, right? So the word reflects the real life context. Similarly, we won't see a tree that contains a loop like this. So anytime we have something with these three features, so a cycle, multiple edges, or loops, this thing will cease to be a tree. A tree means that our network diagram, or part of the network diagram, will just look like this. It will just look like all of these sort of different parts, these edges going off in different directions, but containing no cycles, multiple edges, or loops. Now, a tree with n vertices, so n number of vertices, will have n minus 1 edges. Okay, and we'll look at this in the next example, but this is an important kind of piece of information that we should discuss. A tree with n vertices will always have n minus 1 edges. So there'll always be one less edge than the number of vertices in the network diagram or the tree. Now, a specific spanning tree, the point of drawing a spanning tree is to connect all of the vertices of a graph. We're going to talk about minimal spanning trees a lot more in the next video, but just think of a spanning tree as a tree that connects all of the vertices of a graph. Now, in this example, we're to find two spanning trees for the graph shown opposite. Now, you can see in this graph, you will have a couple of bits that sort of cross over and all of the vertices are connected, but it's not a minimum spanning tree. We just want to connect each of the vertices and just make sure that they're there. And we see here as well, we have a cycle here, for example. We also have a cycle here. So this is a network diagram, but it's not a spanning tree. Now, with a spanning tree, we just want to connect a couple of the vertices. So a way we can do this is we can connect, for example, A to E, A to B, B to C, and D to C. Okay, now we have a minimum spanning tree. I'm going to draw this underneath here. We have E, so we have a spanning tree, I should say. Connects to A, which connects to B, which connects to C, and that connects to D. Now, remember, we said that a tree with n vertices has n minus 1 edges. Let's just count this. So we have 1, 2, 3, 4, 5 vertices, and we have 1, 2, 3, 4 edges, okay? And this kind of makes sense, right? That we'd expect one less because we just want to connect all of these up in one way. We don't need to reconnect D to E because we already have edges connecting up all of them. Remember, a tree contains no cycles, so we don't need this last connection. So in order just to link up all of these vertices together, we need one less edge to make sure that they are all connected in this way. Now, looking at another example over here, we just want to draw a second spanning tree. So I'm going to do this in a different way. Let's connect B to E, E to D, B to A, and B to C. And we'll draw what this would look like. So we're going to have E over here. We'll have D down here. We'll have B over here. We have C down here. And we have A up here. So this is another spanning tree of this graph. And you'll notice, even if you pause this video and have a go at drawing up your own, there may be a number of different spanning trees we can draw for the graph opposite, the graph over here. The main thing we have to consider is that all of the vertices of the graph are connected in one way to another one, and that the number of vertices that the graph has, we should expect one less edge. And we can just verify that here. We still have our 5 vertices, and we have 1, 2, 3, 4 edges here. So this is how we can draw a spanning tree, and this is how we define a spanning tree in the context of network diagrams. In the next video, we will look more at drawing up minimum spanning trees and defining those explicitly. But thank you so much for watching. I'll see you next time.